Hello everyone, my name is Maaz and this is our final video for a Discrete project. In this project, we analyze the consumer price index or CPI data of major Pakistani cities to study how similar their price behaviors are. CPI is one of the most important indicators of the cost of living, and by comparing cities, we can understand how regional markets move together. Our goal was to compare cities across multiple years using cosine similarity, which tells us how similar the price patterns of two cities are regardless of scale. We take these similarities to build networks where each city is a node and edge represents similarity above a threshold. Using these networks, we apply centrality measures to identify influential cities and examine how similarities change over years. The final result is a combination of mathematical modeling, network theory, and data visualization.
Every city first convert the CPI data into numerical vector. These vectors represent average monthly prices within each of the seven categories such as food, staples, meat and dairy, utilities and transport and so on. By structuring the data this way, every city gets a clean and consistent price profile. These vectors are backbone of all similarity calculation and allow us to compare cities in a meaningful mathematical way. To make the analysis more accurate, we applied a detailed pre-processing pipeline. We normalized the product name, fixed inconsistent city names, removed outliers, filled missing values using category level means, and finally mapped each item into one of the seven economic categories. These steps make sure that all cities are comparable and that non-obviously or inconsistent data affect the network result. To compare two cities, we use cosine similarity. Cosine similarity measures the angle is the angle on between two city price vectors, not the raw scale of price. This is useful because two cities can have different price levels but still follow the same pattern of price movement. So cosine similarity helps us detect structural similarity, not just expensive to cheap, which is exactly what we need for economic network analysis. Once the similarity matrix is computed, we convert it into network using threshold like 0.6, 7, and 8. At a low threshold like 0.6, the network becomes very dense with many connections. And as we get start to higher on the threshold, we start to see lower connections. These threshold adjustment let us examine more broad and deep level of similarity across cities. Our Python code is designed in a modular way. We separated components for loading clean data, computed network similarities, and computed similarity matrix building weighted and unweighted graph, calculating centrality scores and generating visualization like heat maps and network plots. We also created menu. We allow user to basically choose categories, years, and threshold. This structure make the code more scalable and easy to understand. This project mainly relies on a few core-based structure, Panda data frame to store CPA data, NumPy for arrays, network graph objects to build network, Python libraries for category and city mapping. And the core function of this is a function used for clean and normalization data, similarity function that computes cosine matrix, a graph building function that creates network based on threshold, certainty function that computes degree closeness between us and eigenvector scores. Moving on to the code. From what we said, this function converts the CPI data into structured vectors for each city. Rows become cities and columns become products, and the value are average prices. This is used to pre-process the data. The pre-processing function mixes, merge, normalizes products names, standardized prices, and automatically maps each project into one of the seven CPI categories. This is the cosine similarity, which is used to measure the angle between two prices. Vector these functions standardizes the data, computes cosine similarity for all pairs of cities, and returns the similarity matrix. This is a graph from similarity. This function converts it into similarity matrix into a graph. Only edges above threshold like 0.6, 7, or 8 becomes actual connection. This is well structured into our class called CP analyzers, as you can see here. Yeah, it's where we process everything, connect everything, loading data, computing similarity, building graphs, and producing score. Thank you. Now the next member will continue.
Let us explore the visual results, starting with the heat maps. In the food stamps category 2024, Islamabad, Rawalpindi and Lahore form a strong similarity cluster, which scores around 0.77 to 0.8. Other cities like Larkana, Sakkar and Bahawalpur have moderate similarity, showing regional patterns as you can see in these heat maps. Next, if we move on to the cosine similarity networks, like here, which shows highlights the effect of thresholds. Here I have used the threshold of 0.6. Here you aren't able to visualize all the edges, but there are edges between these nodes which aren't visible because of the large size of the node. But here you can see at 0.6, here you can see Islamabad, Kota and Rawalpindi together, Sakkar and Bahawalpur together, and Lahore, Sialkot and Gujranwala are together. But if you move on to 0.7 threshold, you can see only Islamabad and Rawalpindi are together here. Bahawalpur have moved apart from Sakkar and Quetta have moved apart from Islamabad and Rawalpindi. We show that the weaker edges have disappeared. If you move on to 0.8, only the strongest connection remains. Islamabad and Rawalpindi dominate while the Sialkot, Gujranwala and Bahawalpur become sparsely connected. Now, if we go back and check, now the next thing is comparing weighting schemes. Here I have the weighting schemes. First of all, we will compare the equal weighting. In equal weighting at the threshold of 0.7, top cities are Islamabad, Lahore, Rawalpindi, Thakkar and Bahawalpur, reflecting consistent similarity across categories. Now we move on to entropy-based weighting. So cities with higher price variability like Bahawalpur and Sakkar gain influence while Islamabad and Rawalpindi remain strong at a threshold of 0.8. As you can see here, both have a score of 0.7569 and 0.7139. Lastly, we have correlation based weighting. So here is the correlation based weighting where we can show all the zeros because the centrality patterns are highly correlated across categories, making the scores collapse. Overall, these visualizations, which are heat maps, networks, and weighted rankings, allow us to see which cities are more central, how cluster forms, and how influence changes with thresholds and weighting schemes. So this is all for the visual part of the video.
Now I will discuss about the centrality measures and how they help us identify influential cities in Pakistan's CPI network. In our system, we compute four centralities that include degree betweenness, closeness, and eigenvector centrality, and then combine them using different weighting schemes. As you can see that this is the result of our code, and in the equal weighting at threshold 0.7, the top three cities are Islamabad, Lahore, and Rawalpindi. This matches their strong centrality structure. These cities have high degree centralities because they connect to many others, and they also have good eigenvector scores due to being part of dense clusters. Now, in the correlation based weighting, we can see that the output collapses to zero. This is because that the centrality vectors across categories are almost perfectly correlated. So mathematically, the correlation matrix becomes redundant and the weight for each category becomes zero. Now, with inotropy weighting, uh, at threshold 0.8, we can see that the Islamabad rises to 0.7569 and Rawalpindi to 0.7139. This tells us these cities show significant diversity in centrality across categories, which inotropy rewards. Now, in the next part, I will discuss about the temporal network analysis. Uh, as you can see that in the network part, uh, when we compare different years, uh, we can see that uh, the network gradually become denser. This means cities are becoming economically more similar over time. When I select compare threshold, the program displays the output by showing the chart in which we can see that at 0.6 The edge count is the highest, meaning the similarity network is still dense and many cities are connected. Now at 0.7, the edge count drops significantly. This is where we start seeing meaningful structure clusters like Islamabad, Lahore, Rawalpindi remain connected while weaker similarities disappear. At the zero point 0.8, only the strongest relationship can survive. The network becomes sparse and reveals the deepest economic bonds between the cities. You can clearly observe the visually. At lower thresholds, almost every city is connected. At mid threshold state, uh, only the uh, uh, only the states with the clusters dominate, and at high threshold, only a handful of edges remain, showing the backbone of the CPI centrality of network, similarity of network. Uh, Now, at last, I will discuss about the uh, key takeaways and our future work. First, Islamabad, Rawalpindi, and Lahore consistently rank among the uh, most influential cities. This is visible across almost all the weighting schemes and thresholds we have seen. Secondly, the inotropy weighting scheme, we can see that the sometimes Salcott rises to top three uh, due to the uh, volatile pricing behavior. Third, the temporal structure shows increasing integration from 2023 to 25. Similarities rise across almost all categories, indicating the markets are becoming more uniform. Now, in terms of future work, our model can be extended to incorporate policy simulations, predictive forecasting, and additional years of CPI data. We can also integrate machine learning models to predict future CPI similarity networks and identify early signals in inflationary pressure. Overall, this approach gives us a powerful analytical tool for economic comparison, policy making, and understanding regional market stability. Thank you.